and gentlemen, good evening. Welcome back to the ICBS International Congress of Basic Science 2025 Physics Night in Peking, China. I'm your tonight's host, Grace Liu.
Thank you, Grace. Let me also welcome our distinguished guests and, of course, give our warm welcome to our friends online in front of the camera. I'm Fotis Koutroulis. I'm a postdoc at the Theory Division in Institute of High Energy Physics, and I will be your co-host tonight.
Thank you, Fotis. As we promised last year, we're gathering here again for this grand, significant event. We see many new faces as well as familiar faces.
Exactly, and it's always a great pleasure to meet all these new and old faces, of course.
As we kick off tonight's festivity, please join me in welcoming the chairman of the conference, Chair Professor of Tsinghua University, Foreign Academician of CAS, Professor Xingtong Yao, to the stage to give us the opening speech. Welcome.
Welcome.
Ladies and gentlemen, it's my great honor to be here to say that we have been very successful in these last 2 days. The Congress of Fundamental Research has been focusing on interaction between 2 and 3 fundamental fields, physics, math, and also engineering. And we have broadened our subject slightly this year. In the last 2 years, we have mostly focused on theoretical science. But we decided this year that without experiment, without technology, theoretical science cannot be as good as what they are. And also, we see how freely can be applied to develop into excellent technology. So it is a truly interdisciplinary cooperation between people from different areas. And I'm very proud to say that we have chosen the excellent candidate for the awards. And we see that from Sam Deng, who I know very well for a long time, but after looking at what he has done and also listening to what he did, I found that he's truly marvelous, far more than what I knew before. And these are truly fundamental works. And of course, David Close, who I know even longer. I learned quantum field theory from him when I was in Princeton, but I was a poor student. Still, I admire what he has done, and I learned some of the technology from him, make me to move a little bit better than what I would have been as a mathematician. But I think it's a very important interdisciplinary study for myself. And then, of course, in mathematics, we have Morley, who is a great algebraic geometer, studying whole subject in high dimension in the modern days. And then we have George Lussick, who is a great representative of physics, also bridge between physics, math, and geometry and topology and all that. So these are very interdisciplinary representative leaders in the subject of mathematics and physics. And in engineering, last 2 years, we have majorly focused on information science and AI. I think there's a limit to what AI could go in terms of depth and all that. You will be spectacular in the future, but for the past accomplishment, I think we have many, many truly important scientists who has made important contributions. So, of course, Bob Targent has been a great mathematician who has developed into algorithms and revolutionized computer science. But this year we decided to have some engineer or physicist who has made contribution to fundamental technology. So that's why we are extremely proud to have Steve today, and I must say Steve Chu, I knew his name and also met him for more than 30 years. Still, after listening to his talk this morning, I really admire what he has done. In many ways, reminiscent to my childhood also. He has a tough household, tough father and mother who expect him to grow in a Chinese way. So am I. But I enjoy to have such a tough parents. I don't know if he enjoyed it or not. But still, I think looking at what he has done, curiosity driven him so strongly that from physics he went into technology, make a major breakthrough and change the subject in a fundamental manner. All these, I think, are important, especially for our young scholars, students. From then, we will work very hard because we like it ourselves. And I think it's a very important thing. And also for the government, I think we should always respect subjects that are driven by curiosity. Once we are interested in the depth and the beauty of nature, the accomplishment will be there, either in understanding the depth of nature or the power of technology. As Steve pointed out, technology is one of the major things for discovering deep science, and so is the other way around. Namely, truly beautiful subject will lead the development of technology. So I think we should honor both sides. And I wish from now on, our Congress will honor both sides. And I'm very happy to say that. And I'm very happy to have the Physics Institute and High Energy Physics and all of our physics colleagues are very happy to see this development. So this tonight was contributed by them, both in terms of human resources and also money, finance, which is an important part of our conference. And I'm very happy that they were able to take care of our most prestigious friends from physical science. And thank you.
Thank you, Professor Yao. Thank you for the interesting and inspiring speech as usual. Now let's invite the Director of the Institute of High Energy Physics, Professor Jun Tao, to the stage to give us his speech. Welcome.
Ladies and gentlemen, good evening. It's my great honor to welcome you to the third edition of Physics Night, hosted by the Institute of High Energy Physics, or IHF, Chinese Academy of Sciences. 2025 is a landmark year for physics. It has been 120 years since Einstein gave us the relativity, and 100 years since quantum mechanics was born. This was not just theories that changed how we see the universe. They literally reshaped human civilization. And a century later, after numerous profound explorations, their impact touched everything in our daily lives and technology. As we stand on the shoulders of these giants, we at IHF are proud to carry forward this legacy of exploration. For over half a century, our institute has been at the forefront of large-scale scientific endeavor. IHF has constructed and operated China's first large science facility, the Beijing Electron Positron Collider, since 1988. Up to now, this collider continues discovering mysterious phenomena in the Chang Park energy region. IHF has a highly successful neutrino research program with Debye and Juno experiments. We also actively participated in LHC experiments in Europe with increasing contributions. Our contributions span across multiple frontiers. We study astrophysics using satellites such as InSight, GCOM, IceNetPro, SWARM, etc. We host the most powerful cosmic ray experiment on the ground, NASA, and ground-based cosmic microwave background experiment, RDCDT. Meanwhile, we operate a simulation neutron source in South China and are building the world's brightest synchrotron radiation light source, located only several kilometers away from here. Going forward, we will keep tackling the toughest challenges, designing next-generation experiments, and working globally to expand the human knowledge. And our vision is clear: to push the boundaries of fundamental physics and answer great questions of our time. Tonight, as we celebrate the Physics Night for the third time, we gather not just to reflect our past achievements, but to chart the course for future discoveries. This evening promises rich discussions on emerging theories and experimental frontiers, bring together established leaders and the next generation of physicists. Before we begin, I would particularly recognize our international colleagues that travel far to join us. Your presence embodies the collaborative spirit that drives modern science forward. May our quest for scientific truth never cease. May Physics Night inspire us all. Thank you and welcome to Physics Night 2025.
Thank you, Professor Jin Cao and Professor Yao. They just kick off tonight's festivity by their brilliant speeches. Now, 2 more keynote reports are coming, and then we're going to invite Professor Anthony Zi, who's not only a great scientist, but also a great science popularizer, a great host to host this session. Welcome.
I'm honored and delighted to be given the job of introducing our 2 distinguished physicists this evening, Stephen Chu and Hiroshi Oguri. And Stephen has made my my assigned job of introducing him infinitely easier since his speech this morning, his lecture this morning, included a lot of very interesting biographical details. I think it should be made into a book to inspire Chinese Americans because Chinese Americans are a unique group. These are, I'm referring to people of Chinese descent growing up in the United States, especially the younger generation. So I believe that Stephen is probably, is surely one of the most successful Chinese Americans in history. And certainly the only cabinet level official in the US government under President Obama. So please welcome Professor Stephen Chu, whom I have admired for years.
Okay, I'm delighted to be able to talk to you again, and I hope I won't bore you too much in by 30 minutes. I was originally going to talk about 2 great research universities, but I remember that I came from University of California and Berkeley Lab, so I have to mention that. And so let me just begin by saying that scientific progress doesn't really often happen as a lone explorer working in seclusion. That's an image that we have of Albert Einstein, but most of the time it's in teams of people working together. And in the history of many of the great scientific revolutions, for example, quantum mechanics was developed largely in academies in Göttingen, Heidelberg, Copenhagen. Structural biology in Great Britain, the Laboratory for molecular biology, and also at Bell Laboratories. And I was very fortunate in my life to spend all my time at these three institutions: Berkeley, Bell Labs, and Stanford. So I want to go through what was so successful about these research institutions that made them possible, and perhaps is it possible to replicate them today. So I'm going to put it in terms of a few lessons. So lesson number one is to maximize the chance for making a great discovery by developing and using new technology, which was a large part of my theme of today's talk. But I'm going to put it in a context of these institutions. So this is a picture of the University of California, Berkeley, a beautiful campus overlooking the Golden Gate Bridge. And during that time, the first Nobel laureate at Berkeley was a person by the name of Ernest Lawrence, who invented the cyclotron in 1931. And so he was, I think at that time, maybe 30 years old, very, very young. In fact, I see it now, he's 38 years old, with the first cyclotron. So it's one example. In terms of the laboratory for medical research, this talk will have a lot to do with biology, structural biology. For the last 30 plus years, I've been doing biology, and I got to know many of these people personally, not those people, I'm not that old. But in any case, it started with X-ray diffraction at the Cavendish Laboratory, the physics laboratory in University of Cambridge. Lord Rutherford was the Cavendish Laboratory, and he was succeeded by William Bragg, Lawrence Bragg. And so the two Braggs shared a Nobel Prize together. To remind you of what was happening during this time, in 1948, this bunch of really physicists started to research using X-ray crystallography. And in 1953, a miracle happened where Watson and Crick determined the structure of DNA. Now, I should mention that it wasn't, it was just a few brief images. It was mostly a chemical model based on the knowledge of the chemical bond by Linus Pauling. And so they had a very little glimpse of what was going on. And then Prutz also showed, Max Prutz showed that you can determine the three-dimensional structures of proteins using heavy metal substitution. So this is a picture of Watson and Crick and Maurice Wilkins, who shared the Nobel Prize. There's, of course, a significant fourth person, Rosalind Franklin, who sadly died before the recognition of this, but it was a problem because she should have been the third or fourth for sure. You might notice, I just have to tell you a little funny story. James Watson, in his book, The Double Helix, thought that Rosalind Franklin was very homely, and I don't know how he can decide she was homely and he was not, but never mind. Anyway, that's the famous X-ray picture that she took. So, in the history of the Cavendish Laboratory, Neville Mott, a Nobel laureate, succeeds Lawrence Bragg, and he thought these physicists turned into structural biologists were not really genuine physicists, so he actually banished them from the Cavendish Laboratory. And so these people were in this little hut outside the Cavendish Laboratory. That's a group of them. And it was funny because many years later, in 2003, I was giving a series of lectures at Oxford and then a series of lectures at Cavendish Lab in Cambridge. And they said, well, we wanted you because you're a physicist going into biology and we want to know how to go into biology. And they had it all. And in fact, the laboratory was just across the city in Cambridge, which means it was about an hour drive through the small town. But anyway, it was ironic. Let me continue about this. Oops, why is that? This is a history that Max Proust and others convinced the Medical Research Council of Great Britain to make a new laboratory for molecular biology. And this is John Kenderew, who Nobel laureate, demonstrating his model of myoglobin to the Queen. And one of the ladies in waiting said, "Oh, I had no idea we had all those little colored balls inside of us." Anyway, the history of the Cavendish Laboratory and LMB, as these are a whole bunch of Nobel laureates who have gone there, hardcore physicists, but then going and evolving later. And so this was a spectacular place in that these are the Nobel laureates, and the names on the right were people who were trained in the Cavendish Laboratory during those times. Okay, so let's talk about Bell Laboratories. Alexander Graham Bell invents the telephone in 1875, files a basic patent, and by 1900, there were 6,000 telephone companies in the United States, and half of them were Bell competitors. That sorted itself out. There's a picture of Alexander Graham Bell, and he's the one with the beard. You guys are not laughing at my jokes. I'm going to have to stop making jokes. And anyway, deep in the culture of Bell Laboratories, actually starting with Alexander Graham Bell, because he was a very serious scientist, inventor, they hired a physicist, the second PhD physics at Harvard at the time. He joins Bell Laboratories. And then he convinces the president of AT&T to allow him and other people to study problems which, quote, require a solution but are not studied as they will not lead to any direct advantage to ourselves. And way back when, in this time, in the 1880s, AT&T Bell Laboratories bought into this. It was remarkable. And so this is more of the history of Bell Laboratories. And in 1914, they had 550 scientists and engineers. And then Bell Telephones Laboratories was formed in 1925. And then in New York City, they finally moved to a suburb of New Jersey, maybe 40 minutes from New York City, called Murray Hill. This was a remarkable place. The first Nobel laureate was Clinton Davidson, who worked with Bell Laboratories during World War I, and he was so impressed with the place that even though he had a professor appointment, assistant professor at Princeton, he decided to stay there. And in 1927, working with a custom-made vacuum tube, he and his technician, Lester Germer, were bombarding electrons with nickel crystals, and they saw diffraction. And that was the confirmation of the wave theory of matter espoused by de Broglie that later germinated into a full-blown quantum mechanics. Oops, sorry, I don't know what happened. Bill Shockley joined, he was a brilliant theorist who joined Bell Laboratories to work with the great Davidson. But then they said, you know, you are very conversant in modern quantum mechanics, and we want you to lead a new department in semiconductor physics. So, and that's what he did. And you have this famous picture of Bardeen, Bertin, and Shockley leaning over and posing for the transistor. I have to say that Shockley was a theorist, Bardeen was a theorist, and Bertin was the only person who did the experiments. So why is Shockley doing this? Well, he was their department head. In fact, his name is not on the patent of the transistor. Bardeen and Bertin, without permission, just went off and invented the thing. He found out about it, became completely incensed. How dare you invent something like this when I was supposed to be your department head and do this? And so he got so mad, he holed up in a room for the next couple of days and developed the quantum mechanical theory of semiconductors. So he deserves to be on this Nobel Prize, but he was not part of the patent. And this is a picture of the first transistor, very impractical. It's a pretty ugly looking thing that only a mother could love. But in any case, this rich history was developed, and we have other Nobel laureates. Phil Anderson, who is a legendary condensed matter theorist, who got a Nobel Prize for his theories of glass and magnetic materials. The laser and maser, Charlie Towns was at Columbia, but he was also consulting at Bell Laboratories. His student who made the first maser with Charlie Towns, Jim Gordon, became an employee at Bell Laboratories. Art Shallow, Charlie Towns' brother-in-law and the co-inventor of the laser, became employee of Bell Laboratories. Robert Wilson, Arnold Penzias came to Bell Laboratories to use the very sensitive radio detectors to do radio astronomy. And so if you look at the history, if one looks at the history of Bell Laboratories, it's stunning. From the 1920s, the invention of negative electronic feedback. 1930s, radio astronomy, the first binary digital computer, diffraction of electron waves. The asterisk mean it got a Nobel Prize. The photovoltaic silicon cell was invented at Bell Laboratories. The transistor was invented at Bell Laboratories. Information theory was developed and invented at Bell Laboratories. The laser, the first transatlantic cable. And you just go down the list, CCD, Unix, molecular beam epitaxy, the discovery of 3-degree blackbody radiation, C programming language, digital signal processors, the fractional quantum Hall effect, cell phone technology, all invented at Bell Labs, fractional quantum Hall effect, laser cooling, trapping, quantum dots. Wireless communications, the first computer algorithm, Shor was at Bell Laboratories. So this place had 11 Nobel Prize winners and 5 Turing Award winners. And so let me try to describe a feeling for what it was like. So I'll turn first to a quote from a mathematician named Ronald Graham, who worked at Bell Laboratories for most of his career. And he's describing what it was like. He said, typically, it takes someone 1 or 2 years to learn the ropes well enough to get plugged into various networks around here. One might mention a few problems that are floating around. The one difference between Bell Labs and a university is here, more or less, everyone comes in every day, the office doors are open. There's a lot less feeling this problem I'm working on is my problem, and that I'll tell you about it when I've dotted all the I's and crossed the T's. You had a half-baked idea, a quarter-baked idea, and you talked about it because you weren't worried that people were going to steal a precious idea. Why? Because the idea was so rich in the air of Bell Laboratories, you just had to decide which one you wanted to work on, and as you co-develop these ideas. So it was a very different place than anything I knew before that. And so, for example, when I was hired in 1977, 78, there were a bunch of people hired my same year. Doug Osheroff, me, Dan Sui, Horst Stormer, Bob Laughlin, all got Nobel Prizes. We were hired very young. They didn't hire us, and we had already done the work. We had done nothing and did it there, which is stunning. And so in my Nobel autobiography, I write that I was one of roughly 24 brash young scientists who were hired within a 2-year period. We felt like the chosen ones, with no obligation to do anything except the research we loved best. The joy and the excitement of doing science permeated the halls, the cramped labs, and office cubicles forced us to interact with each other and to follow each other's progress. The animated discussions were common during and after seminars, at lunch, and continued on the tennis courts and at parties. So it was truly a remarkable place. During my time at Bell Laboratories, there was an antitrust suit brought by the government, and AT&T decided they were going to shed, by this time, they had grown to 24,000 employees. The budget was $2 billion a year. That's a significant budget for a research company. And as part of the settlement, AT&T agreed to divest itself from the Region Bell operating companies. And everybody at the time said, if you do this, Bell Labs is at risk. And it was, I joined Bell Labs in 1978 and left in 87. And I remember on the day they announced the breakup of AT&T, I thought the breaking up of AT&T was the saddest day in the history of industrial research, and I still think that. It was really quite tragic. All right, lesson number 2. I learned there, you try to hire people better than you. The people you hire are your protégés, they're not your assistants. Assistant professors were your protégés, they weren't professor assistants, and their success becomes your success. And when I became a manager after 5 years, the department head at Bell Labs, that's how I looked upon the people in my department. They were not working for me, I was working for them. My job was to make them successful. And you're constantly on the lookout for talent, even if you're not allowed to hire. And the best people I saw would hire the best people. And I found later in life that mediocre people hire people less talented than themselves. And so the expression is A's hire A's and B's hire C's. Let me give you an example of the culture I grew up in. It was Ernest Lawrence. And Ernest Lawrence surrounded himself, was able to attract spectacular young people. And so in front of the 60-inch cyclotron, there's an all-star cast of these people, including 4 future Nobel laureates and Robert Oppenheimer. And there's more of them posing before one of the accelerators. Also during this time, Lawrence was able to get Ed McMillan and Glenn Seaborg, who got a Nobel Prize for discovering transuranic elements. Melvin Calvin, it was interesting with Melvin Calvin, they had this cyclotron, they had radioactive isotopes of carbon-14, and Lawrence said, well, maybe we should think of doing some biology with radioisotopes of carbon-14, and off it went. And so it was said of E.O. Lawrence, his cyclotron is to nuclear science what Galileo's telescope was to astronomy. He had the vision to glimpse at the limitless nature of the horizon and the generosity to make room for others. His personal credo was, there's enough research for all of us to do. He interceded with his rare persuasiveness to create new facilities for worthy projects. He rejoiced jubilantly in the success of others as his own. As a result, the careers of many scientists, including my own, not me, but including my own, are founded on his large contribution and his generous nature. Indeed, so great was the opportunity he created, he was influential in training a significant portion of the present core of nuclear scientists, said by one of his protégés, Glenn Seaborg. And this is the impact he had on the institution, his leadership and his vision and his generosity. Another lesson, hire people not representative of a field, let them spread their wings. And so Max Perutz, a Nobel laureate in Laboratory for Biology, described one incident. He said, a delegation from the Soviet Union appeared in Cambridge demanding to see the Institute for Molecular Biology. They wanted to know how I planned our successful research unit. Imagine that I recruited an interdisciplinary team as Noah had chosen the animals for his art, 2 mathematicians, 2 physicists, 2 chemists, 2 biochemists, 2 biologists, and told them to solve the atomic structure of living matter. They were very disappointed. They were disappointed that the unit had grown haphazardly and that I left people to do whatever happened to interest them. That was it. No plan. And so at LMB, Max Perutz, John Kenro, Francis Crick, Jim Watson, all these people were joining. Bell Labs is the same sort of vision, hire the best people, leave them alone. And in 1904, AT&T hired Frank Jewett, who was a student of Albert Michelson, I think was the United States' first Nobel laureate. And he was a friend of Robert Millikan. And these people began to feed into Bell Labs their best students, which is remarkable. Now, returning to Sidney Brenner, he was an advisor to 2 other Nobel laureates, and he would say, nobody was a professional. We were all talented amateurs. We attracted the best, and our job was to create people better than ourselves and other senior people. The best, most daring, are the youngest, but then become middle-aged. What happens after 6 years? Good question. So more about amateurs. I quote someone else, "When the war finally came to an end, I was at a loss as to what to do. I took stock of my qualifications, a not very good degree, a knowledge of certain restricted parts of magnetism and hydrodynamics, neither subjects which I felt the least bit of enthusiasm. Only gradually did I realize this lack of qualification could be an advantage. By the time most scientists have reached the age of 30, they were trapped by their own expertise. I, on the other hand, knew nothing, except for a basic training in somewhat old-fashioned physics and mathematics, and since I essentially knew nothing, I was had an almost completely free choice," said Francis Crick. I tried to emulate that. I know nothing, and I have a free choice. Max Pruss, in setting up the organization, wanted it very, very lean. And I'm not going to read you this, but fundamentally he said, they wanted to make me director. I didn't want to be director, so I formed a little council of 3 other to-be Nobel laureates, and we rarely met. And he said, seeing the chairman stand at a laboratory bench or an X-ray tube rather than sitting at his desk set a good example and raised morale. Really amazing. And the LMB was founded on long-term funding research, and it took Max Pruss 23 years to solve the structure of hemoglobin. And many of his colleagues, chemists and biologists, thought he was wasting his time. And so in this atmosphere, you didn't have to justify what you were doing for 2 decades. Bell Labs, you couldn't do that. If you didn't make progress in 2 or 3 years, someone was breathing down you. Well, what is happening? But never mind. I did say, and this is another thing, instill young hires with high expectations. So I'm writing my experience at Bell Labs. Bell Labs managed to supply us with funding, shield us from extraneous bureaucracy, and urge us not to be satisfied with doing merely good science. My department head told me to spend my first 6 months in the library and talk to people before deciding what to do. Later during performance review, a very rigorous review, he chided me not to be content with anything less than, quote, starting a new field. I was very cheeky, so I said I would be happy to start a new field, but I needed a hint as to what new field he had in mind. Anyway, that was an expectation, of very high expectations for all the young scientists. And another thing is that young scientists should have courage, even when the older people are telling what they're doing was silly. And I got to know Charlie Townes reasonably well. He was the co-inventor of the maser and the laser in the early 20s. And he was visited by the chair of Columbia Physics Department, who at the time was Polycarp Cush, who was the advisor of my thesis advisor, who got a Nobel Prize, and Robbie. So Cush and Robbie are visiting Charlie Townes. And he said they believed he was wasting department resources and tried to convince him to give up what he was doing. Charlie didn't listen. He had tenure. Robbie and Cush had to let him continue. So if you think about this, they said, no, what you're doing is down to fail. And he said, it's okay. They would leave one alone. And it wasn't just locally. Niels Bohr and John von Neumann also thought the maser couldn't work even after it worked. And he said, that's impossible. Well, anyway, so don't listen to older people. What else could I say? Lesson number 3, good people stimulate each other. And Bell Labs management helped connect us with each other at lunchtime, as I said before. It was a major technological event. You go down, I brought my sandwich with me, but nevertheless, I trotted down to the cafeteria, and for an hour, hour and a half, you engaged in what's new conversations. And it really worked this way. And so, and Max Pruss, who was designing the LMB, said, experience has taught me that the laboratories often fail because their scientists never talk to each other. Most laboratories hold seminars where scientists report their work, but they're often attended by only those scientists in their own group. To ensure that everyone was aware of all the work of the lab, Francis Crick, instigated an annual week of seminars which used to be known as Crick Week, to be attended by all the members of the laboratory. These are dominated by his searching questions and sharp comments. So again, the leadership forced communication, and then once it was forced upon you, people realized it was a good thing, and it carried on naturally. And Sidney Brenner writes, everybody worked in the lab, flies, rats, physicists, chemists, all going in the same direction. I'm not sure if the rats and flies were actually going in the same direction. But in any case, we attracted an extremely talented group of postdocs. Turf was not divided, and they could do what they wanted to do. All directions came from science. We did not build machines and wait for people to come. Central important problems is what unifies people from different disciplines. Improvisation needs to be encouraged. For a culture prep machine, I didn't have the resources, so I talked to the company and given me a washing machine to grow bacteria. These are quotes. I was talking to them. I was writing this down in preparation for a talk about this. So anyway, I'm going to conclude and about my experiences at Bell Labs and also Berkeley, Lawrence Berkeley lab. And so in 1988, I was being recruited to go to the University of Chicago to start a new institute that linked physical science with medical sciences, with biological sciences. I decided not to go, but I said, you know, this is a pretty good idea. So I gathered 3 other friends, Lucy Shapiro, the head of genetics, Jim Spudich in biochemistry, and Dick Zare in chemistry. And I said, let's meet in my office and talk about this. And so we talked about it for a couple of hours, and we decided that it made sense to build an institute to help unify the biobiology, chemistry, physics, and engineering. We wrote a little paper, 6 pages, and we just sent it directly to the president and provost of the university. We didn't go up through channels, you know, department heads, anything like that. And they read it and said, good idea. And that began the beginning of BioX, which has become a model, I think, for many interdisciplinary units around the world, and also became a model when Howard Hughes Medical Institute wanted to fund a new research institute. They were casting around, and guess where they looked? They looked at Bell Laboratories, and they looked at the LMB, and this was Jerry Rubin. And so he consulted with me, with all the other people, some of the other people, not all the people, a couple of others at Bell Laboratories, people at the LMB, and it became a good model for their set. So I want a good model for their institute, and it's pretty successful. It got its first Nobel laureate, and following the tradition of Bell Laboratories. And so I just want to leave a message to the young people. Sometimes you should act and ask for forgiveness later. I'm reminded of this cartoon I love. It's late at night, and without permission, Rubin would often enter the nursery and conduct experiments in static electricity. He's rubbing babies and making static electricity and sticking them on the ceiling. I thought it was very funny. So to you, don't ask for permission, just do it and ask for forgiveness. So thank you.
I'm extremely happy and honored to introduce our next speaker, Professor Hiroshi Oguri. Now, when the committee that formed the Institute for Theoretical Physics in 1979 decided to put the new National and International Institute of Theoretical Physics in Santa Barbara, they must be able to predict in the future that a certain Hiroshi Oguri would arrive at Caltech and that he would like to visit Santa Barbara. He He's one of our most welcome visitors. He comes to Santa Barbara often, and he brings a lot of great physics to us. Now, in my career, I love to collect people whose careers were different from the mainstream, quite different. And I always thought that people like Rob Phillips at Caltech, who never went to university, but who's now a full professor at Caltech, or Ed Witten, who never took a physics course as an undergraduate, or Maldacena, and the rocket rise of these people are pretty amazing to me. But Hiroshi's story is even more amazing. Apparently, after 2 years of being a graduate student at Kyoto, he told me that Tokyo University offered him a tenure professorship. Now, this completely confused the academic system. How can a tenure full professor and without a PhD arrived, and how can he then still has to go back to Kyoto to study to get his PhD, and so on and so forth. So please welcome Professor Oguri.
Okay. So thank you very much, Professor Z, for the very, very generous introduction. It's an honor to be here to give a talk. I suppose I'm supposed to have a pointer here. So let me see if I can. So this is a test of my competence. Do you see the pointer? Okay, good. So the title of my talk is Toward Unification of Gravity and Quantum Mechanics. So I'm a physicist, and one of the things physics do is try to understand the fundamental laws of nature, and to use that to explain natural phenomena. And so going back to the laws of physics is a sort of basic approach in physics in science. And from this perspective, one of the most fundamental questions in modern science is the unification of gravity and quantum mechanics. And before discussing it, since this is meant to be for young students, I thought I would like to share why I'm interested in it, and then I explain why it's an interesting question to pursue. So this was actually my pandemic project. So during pandemic, I was asked to write some autobiography, and so it was published, and in fact, it was translated into Chinese also a year later. And so if you're interested in this, please consider looking at it. And so I'll tell you one of the story I wrote in this autobiography on why I became interested in physics. So this has to do with measuring the size of Earth from a restaurant. So when I was a fifth grade, probably many of you do, that in school you learn elementary geometry of triangle and circles and things like that. And one of the memorable experience, and in fact this is a photograph of my junior elementary school, there was a telephone tower next to our junior high, our elementary school, excuse me. I was a fifth grader. And my teacher took me to the schoolyard and let us measure the height of this telephone tower. And I was very impressed. You can use this simple property of similarity of triangle to measure the height of a telephone tower. So sometime later, I was having lunch. My parents took me to lunch to this revolving restaurant. This is actually a photograph of the restaurant we were. So this one goes around maybe in an hour and come back to the same point. It's a beautiful view. So I really like this restaurant. And then so by looking at it, you see the horizon. So I got interested in knowing how far the horizon is. So I knew about this similarity. So when I was going around this, what happened to, there is something wrong. Yeah, when I was, my parents and I were having lunch and come back to the same place, somehow I was able to figure out that the distance to the horizon is equal to the product of building height and radius of Earth, and then take square root. So that's called geometric mean. So if you calculate geometric mean, you can, of the Earth size and the height of the building, you can figure out the distance to the horizon. So this is the equation. And, but there was a mistake I was making. I was a fifth grader. So in fact, if you do the more careful calculations, there is a factor too. But I was a fifth grader, so you can forgive me that. But there was a problem because, well, I thought I could figure out the distance of horizon, but I didn't know the radius of the Earth. Okay, so what should I do? So, well, I was looking at it and I realized that, well, if you actually write this equation in the same way, the same equation in a different way, then you can actually, by knowing the distance to the horizon, you can actually estimate the size of the Earth. Well, I have to confess, this might not be very original because by that time, I have read about some of the accomplishments of Greek scientists and mathematicians. So I heard the story of Eratosthenes. So I might have connected to that, but anyway, so I had this, and then it turns out that around the horizon was my father's hometown. So I asked him, how far is the horizon? How far is your hometown? He said like 20 kilometers. So I could plug this number into the, I could also figure out the height of building because I was a fan of monster movie. And the monster typically are of the same size as these buildings, and they topple building and do all kinds of things. So I can estimate the height of building by knowing the size of the monsters. And so then I could estimate the size of the Earth. Of course, that was like off by factor. But it was, the number of digits was roughly the same. Of course, I wasn't aware of this factor too. So I was very impressed. Well, size of the Earth is something like very fundamental. But just simply observing a view from the window and doing some very simple calculation by using similarity of a triangle, I was able to determine the size of the Earth. So well, I was very impressed by this, and so that somehow the profound nature of this world can be unraveled through observation and thinking. Okay? So most important message I learned was that there's actually truth in this world, and we can go out and figure them out. So that sort of encouraged me to go into physics. So I entered Kyoto University in grad school, and in 1984, Professor Z gave a very generous introduction, but I was very lucky because I entered grad school in 1984 and to study elementary particle physics. Because it turned out to be an important year. So I want to explain why this was an important year to be in the first year graduate student. So actually to explain that, I have to go back to history 20 years, back to mid-1960s. So the Professor Chu told you about the Lawrence Berkeley Laboratory. And so around this time, 1950 and 1960, the particle accelerator discovered a wide variety of new elementary particles. These particle accelerators are sort of successor of the cyclotron invented by Lorentz. And, but there are so many elementary particles and their properties were very confusing. So in some sense, particle physics was in the state of chaos. And then Yoichiro Nambu came up with the idea around 1970 that this mysterious property of elementary particles could be explained by postulating that all the elementary particles are made of strings. But there was a problem that string theory at that time predicted some particle that had not been formed in particle experiment, and that had very weird property, and so it was very confusing. And then 1974, 4 years after Nambu proposed this, Tamiaki Oneya, who was still a graduate student in Hokkaido University, discovered mathematically that this new particle that was confusing actually have the property of mediating gravitational force. And Joel Sharp and John Schwartz independently discovered this. John is my colleague at Caltech, and proposed that, that it can be used to unify all the forces of nature because it includes gravity, and construct ultimate unified theory. So John used to say that when I made this discovery, I decided to devote my life to study string theory. However, there was a problem. That is that string theory at the time was actually flawed. as a model of elementary particles. There are like many fundamental properties of electrons, or even string theory, even those simple property of electron string theory cannot explain. So in the meanwhile, remarkable discoveries were being made at the forefront, the other front of elementary particle physics, such as proposal of Kobayashi Masukawa theory, and discovery of asymptotic freedom in QCD, for which David Gross was honored for this Lifetime Achievement Award yesterday. And also the discovery of J-psi, which is Professor Tin, was honored yesterday. So all these discoveries were made in different fronts of standard model. So basically, most of the theoretical physicists sort of deserted string theory because of this problem. So John Schwartz struggled for 10 years. Around that, during these 10 years, there are only like a handful of people who are working on this field. I'm from Caltech, so I'd like to advertise that Caltech took a long view and supported the John Schwartz research for these 10 years. And after 10 years, 1984, Michael Green and John Schwartz found a way to use string theory to explain the property of this electron that was confusing. And so that actually started what's called the string theory revolution. And one of the things I was fascinated by was the fact that this rich structure of standard models, such as there are 17 types of elementary particles and lots of parameters and 3 generations. For example, Professor Tin explained in his talk that, his experiment explained why quarks has 3 generations and etc. So those are encoded in this standard model particle physics. But those emerge from in the context of string theory, those all emerges from the geometry of Calabi-Yau manifold. And so I was a first-year graduate student, and I was very impressed by this. And it was a very lucky situation for a graduate student, because since there was nobody else than John Schwartz essentially working on this program, so there are no experts, senior professors know almost nothing about it. So even the first-year graduate student could go into the field and do some, I hope, interesting work. And but you can ask, well, that was quite many years ago, 41 years to be precise. So why you haven't completed this program of unifying gravity and quantum mechanics? And more importantly, as it was said, that produced some experimental verifiable or falsifiable result. So I would like to discuss that, but before that, I need some water. Okay, and so let me continue. So, so I should say that this goal, one of the goals of this direction of research is quantum gravity, which is the unification of general relativity and quantum mechanics. So I'd like to explain the history of this kind of unification in the context. So as I said, in 1974, Yonea and Sharp and Schwartz discovered that string theory contains gravity. So this was actually the first example of mathematically consistent unification of general relativity and quantum mechanics. So you see that it took quite a while. So general relativity was invented in 1915. Quantum mechanics was, actually this is a year of quantum mechanics by UNESCO. And it's about a half century before actually even one mathematical theory of unification of these were achieved. Now let's compare this with another direction of theoretical physics research, which is a unification of special relativity and quantum mechanics. So if you unify special relativity and quantum mechanics, essentially there is a unique theory which does that, and which is known as quantum field theory. And that was invented just a couple of years after quantum mechanics was invented by Dirac and Heisenberg and Pauli. But it took quite a while for the theory to be made sense and become realistic and tested experimentally. For example, even it took like 20 years for mathematical formulation of quantum field theory to become possible by invention of a renormalization method, for which Feynman, Schwinger, and Tomonaga were awarded Nobel Prize. And then it took another 25 years since the invention of quantum mechanics, like the half century, for people to come up with the standard model of particle physics, as I mentioned. It took half century to do that. And it took another 40 years for all the prediction of standard model to be verified, ending with the Higgs discovery. So let's put this in the context. Well, I'm a theoretical physicist. I like to quantify things, and I would like to do back of envelope calculation. So I'd like to quantify how the unification of general relativity and quantum mechanics is more difficult than unification of special relativity and quantum mechanics. So I want to remind you that it took 2 years to propose a unification of special relativity and quantum mechanics, namely quantum field theory. But it took 50 years to construct the standard model of particle physics. And it took 40 more years to verify it experimentally. Now I would like to remind you that it took 50 years to propose a unification of general relativity and quantum mechanics, namely string theory. So from that, I could quantify that unification of gravity and quantum mechanics is 25 times more difficult than unification of special relativity and quantum mechanics. From that, we can do back of envelope calculation to say that it's going to take 1,250 years to construct a realistic model of string theory, and 1,000 more years to verify it experimentally. Now, so in some other country, like across the Pacific Ocean, where people are short-sighted, and I would not give such a talk. But I know that people in China play long game, and that's how you build this wonderful civilization. So I don't think you got scared by this roadmap of 1,000 or 2,000 years. And but I would like to explain a little bit more on why quantum gravity has been so difficult, and achieving that is so interesting. Okay, so over the past 4 centuries, since Galileo and Newton, physicists have gained deeper and deeper understanding of universe. One way that physics developed, there are many different ways. For example, Professor Chu says that inventing new technology is also a very important development, but also the pursuit of unification is yet another important direction for the motivation for physics. So let me review this type of development. So for example, 400 years ago, Newton developed his theory of mechanics, and independently there was a Kepler's law. But Newton realized that you can actually unify the classical mechanics of motion on the Earth and motion of heavenly object. They actually satisfy the same law, so that's why it's called universal gravitation. So that's why it's unification of mechanics and gravitation. There was also magnetism and electricity. Those are known from ancient times. Chinese people knew about magnetism for 3,000, 4,000 years ago by developing compass to navigate the ocean. Understanding of electricity came relatively recently. And, but in the early 19th century, lots of phenomena combining electricity and magnetism was discovered, and it was unified by Maxwell to electromagnetism. And then, but however, there was a conflict between Newton's mechanics and Maxwell's electromagnetism, and that was achieved by discovery of special relativity by Albert Einstein in 1905. But then you have the next task is the unification of special relativity and universal gravitation, and that was achieved by general relativity in 1915. So at this point, you can say that well, all the known classical physics have been unified. So physicists could have, at least those interested in fundamental laws of nature, could have been satisfied with it and went home, except that quantum mechanics was invented about 100 years ago. And so now the next task is how do they fit with each other? Okay, so, well, as I said, the unification of special relativity and quantum mechanics took place relatively quickly, but this project is still ongoing, as I said. Even in now, the mathematical formulation of quantum field theory is still missing, and it's one of the 7 Millennium programs by Cray Mathematical Institute. Okay, so then the next question is what happens to the unification of quantum field theory and general relativity, which is what I have been talking about. And at this point, I would like to tell you, in order to explain why this is a difficult project that requires 2,000 more years to achieve it. I hope it won't take that long, but I would like to explain why this is so difficult. So, since the day of Lorentz, after he invented cyclotron, physicists has started to invent more and more powerful particle accelerator. And by building a more powerful particle accelerator, you can probe shorter and shorter distance. So that's why, for example, China has this wonderful plan to build the most powerful accelerator in the world. And this follows from this kind of equation that higher the energy, the shorter the distance you can probe. However, if you build an accelerator, such an accelerator that reaches the Planck scale of 10 to the minus 35 meter, then, well, Einstein says E equal mc square. So that means that high energy means very heavy state. So eventually, if you build such a high, most powerful accelerator, it's going to construct a black hole at the center of this interaction point. And the interesting thing about black hole is that the size of the black hole, the Schwarzschild radius, or the size of the event horizon grows with the energy, as opposed to become shorter and shorter with the energy. So that means that there is actually an end to this story, that the Planck scale accelerator would not be able to probe distance shorter than this combination of fundamental constant, which is called Planck length. So even if you build more powerful accelerator, there is nothing more you can do. So ever since Newton and Galileo, physicists have understand more and more fundamental laws of nature by looking more and more microscopic world. However, this historical progress, historical march toward more fundamental laws of nature is expected to terminate at Planck scale. So in some sense, this is sort of end of this historical progression. And so that's why it's so special. And so this is the end point. So I apologize for those distinguished professors who don't know what final boss means, but other people may understand. So the reason why quantum mechanics is so difficult is because it is a final boss in our quest towards unification, unify all the laws of nature. And I think at least this direction of going to microscopic world and discover new and more fundamental law will end. Okay, so that's actually more or less all I wanted to say. But there is going to be a panel discussion after this speech where we'll discuss the importance of fundamental science. So I thought I might say a little bit in connection with this and why, especially esoteric research such as this is important for society. So why basic science can be important for the society. So Max Weber is actually one of my favorite thinker in the late 19th century and early 20th century in Germany. And he liked to classify things. So he classified the social action of people into 4 types. And among them, what's relevant here are two rational action. And one is called instrumental rational action, which aim to work out the most efficient way to achieve a particular goal. And the other is a value rational action, which works toward a goal that seems as desirable for its own sake. So these are 2 kinds of rational options. There are actions people do, but in a rational choice. There are also like affectional action, which people do for emotional reasons. But these are 2 rational actions. And these 2 directions are sort of different. But sometimes these achievement of these actions coincide. And in some sense, among these 2 rational actions, I would say the basic science is a value rational action. So in this context, I would like to quote Henri Poincaré. And he wrote several interesting books about how science is done. And this particular book is something I read when I was a high school student and actually had very much impact on me. This was a very interesting book because as you read through it, in the final chapter, he asks the following very important question. That is, what is a variable basic science? And he says that, well, there are many things that you can do as a researcher, but some discoveries teach us nothing beyond the particular fact. But he says, on the other hand, there are discoveries that teaches us new principle and provide new insight. And researchers who must make choice should pursue the latter kind of discovery. So that's sort of his definition of variable science. And you can imagine that the variable science defined in this way will have many broad impact, and some of which can lead to actually applications that can improve human life. So the question is, well, how to do that? So one of the things is actually what Professor Yao said at the beginning, the opening speech, which is that the variable basic science emerges from curiosity, the curious mind of researchers. So this is something that Professor Mori, another Lifetime Achievement Award winner this year, said in one of his essays. So he said that when he was asked to this following question, that is pure mathematics useful for society, then he said that he wrote that he would respond to that by saying that it may not be right now, but it will be useful for in 50 or 100 years. In the meanwhile, the curiosity of mathematicians is the best compass for guiding research. So the very sharp, curious mind of the forefront researcher is the most important guide, especially for this type of value rational action that basic science represents. So that's the kind of message I said. Well, and Professor Mori said that 50 or 100 years, but I think we should maybe also consider tolerating 1,000 or 2,000 years, because I'm sure that even though achieving that goal may take that long, but in meanwhile, there will be lots of new discoveries, both in technology and mathematics, for example, exploring geometry of Calabi-Yau manifold. That will teach us a lot about and provide a new insight our world, both mathematical and physical, and some of which can lead to improvement of human life. So that's a message I would like to tell you. Thank you very much for your attention.
Let's invite, Professor Stephen Chu to host the Q&A part. Okay.
Q&A part. Okay. Well, I didn't realize there was a Q&A part. I enjoyed these two wonderful talks, but let's now invite questions from the audience. Please, especially the young people, after what Stephen Chu said. No? Please. Questions? Well, Stephen, how about a question for you? Yes. What are your suggestions for the development of something like Bell Labs in China?
I think if there's any place that can start a Bell Labs, it would be China. As explained, they have a long view, and they are very good at learning from other people's experiences and taking it further. And so it would be great if China did start a Bell Labs. Why? Because I think it would prod other countries, other places to do similar things. Not because of competition, because actually competition actually invites also cooperation. And so I hope that China does do this.
Okay. If there's no further questions, let me ask Professor Oguri the same question. And how about establish something like this in Japan?
Well, so there is of course economy that is associated to this. I hope that the Japanese government and the industries are also still interested in supporting basic science as a way of sort of exploring new directions. And in fact, these days I'm helping RIKEN laboratories to strengthen its research division in mathematical science and theoretical physics. And there are I just had a meeting with the president of the RIKEN earlier this week, and he seems to be very supportive. So RIKEN is one of these laboratories whose research encompasses from basic science to applied science. So I hope that there will be something positive come out from this. But as Professor Chu says, we need a country which takes long view to support this long game, I think. Thank you.
In my personal experience, I also know that Japanese industries, I don't know if this is still true, but used to support very basic type of research 30, 40 years ago. I personally, I was invited to Hitachi Lab.
That's right.
And I was really surprised that they were interested in somebody like me who knows nothing about applied technology. And they were very generous and so on. So I hope that this tradition continues and maybe also develops in China.
One of the really unfortunate things is American industry used to do this, just not Bell Laboratories or IBM, but General Motors had a great research laboratory. RCA had a great research. Xerox PARC had a great research laboratory. And what happened was the financial analysts said, what have you done for me lately? What have you done the last 3 months? And they became obsessed with quarterly reports. And that really, the long view of industry was then said, no, we can't do this anymore. We have to, look for very short-term, temporary, short-sighted gains. And it's truly unfortunate.
I'm even personally acquainted with this because one of my younger brothers who went to Princeton and Berkeley in physics ended up working for Bell, for AT&T. And in those days when I was working on quantum Hall effect, when I started describing quantum Hall effect to him, he asked if this could possibly help them develop a video camera for $10 less each. So young people, questions? A last chance before, oh, there are people. I see a hand over there.
In the PowerPoint, it said the 1940 and 1950 years, we find a lot of particles. So to research the particle physics is important. But now we don't find any new particles. Why we should to build the collider? For example, the CPC.
Okay, I think Professor Wang Yifang should answer this question, no? Please. Wang Yifang, 为什么我们还要做 particle physics 的？
Particle physics is not just for discovering of the new particles. I mean, this is just a path. It's not the aim. It's not the end. The end is the standard model. The end is the physics, the laws, and the principles of the world. So we would like to understand beyond the standard model, what are the new physics? And indeed, what we learn from the existing accelerators and also the standard model, comparing the data and the theory, we know that this standard model is not the end of the story. It's not the final theory. It's an effective theory up to 1 TeV. So beyond 1 TeV, and most likely between 1 TeV to 10 TeV, there should be no new physics. And that's why we'd like to build this CPC to probe the physics between 1 TeV to 10 TeV and measure the Higgs couplings up to the precision, say better than 1%. So we have a very detailed, precise, and clear physics motivation for this project. It's not just random kind of a goal of building accelerator with high energy and blindly looking for new particles. Sorry, it's not that case.
Anybody else? It could be young or old. I see a hand there. Young or old, and any age in between. There's a hand there.
Hi. Hi, excuse me. I want to ask questions for the professors. So for now, we have like too many subjects, and I want to ask, what do you think is the best way to combine our subjects? Because we have too many specific knowledge now. And if you want to understand the most advanced knowledge for like all the subjects, you need hundreds of years. So I don't know, what should we do to combine them?
Professor Oguri, you want to answer this question, please?
So for example, I like to quantify things, so I would like to quantify it again. So for example, I have been a professor for the last 40 years or so, and then I observed that the question of how long for beginning graduate student to get started with their research. And usually it takes 2 years. When I got started, I was relatively lucky, so I could immediately start research. But typically when I was in the 34 years, it took 2 years for typical graduate student to be able to start doing research. Nowadays, it's still 2 years or so to get started with research. So it is true that as science progresses, we learn more and more things, but we also learn better about how to understand it and how to explain it to students. That our knowledge become also advanced in that sense. Not only we discover new things, but we connect, new discovery connect to new phenomena, and our knowledge is more organized. So somehow we have not hit the wall, which is very promising. In principle, our human brain has been developed because of evolutionary accident. We are supposed to understand what is happening within a few kilometers of the Earth. And it's kind of amazing if you think about it, that we can think about the world of elementary particle and 13.8 billion years ago of the universe. We are not evolved into that. For example, I always tell people about the story of my dog. I have a dog in my home. And she knows that there is a food in refrigerator. But I think she will never understand why refrigerator become cold. And one can imagine that our human brain would eventually hit the wall before we understand the unification of general relativity and quantum mechanics. So this 2,000-year roadmap may be optimistic. We don't know yet. But at least what I can tell you is that given this quantitative estimate of how long the beginning graduate student get started to do research, I don't think we have hit the wall yet. And so it's, yes, please.
I want to add a little bit more to that. I agree with everything you said, but there's something very important. And I think young people, maybe sometimes when they begin to learn science, they make the mistake, I have to learn everything before I can do something. And I tried to indicate it in my talk today that no, you don't have to know everything. You don't have to know anything much at all. Just stumble into it. And so if you think I've got to read all the literature before I do something new, you're going to discourage yourself. When I was an undergraduate, I would go and talk to some professors, I'd see, and behind them was this bookshelf full of books. And I spent a whole year reading volume 1 of Feynman. And then I realized in second year, volume 2, I forgot half of volume 1, or I never really understood volume 1. And I realized 30 years later, yes, it's all true. But I didn't understand volumes 1, 2, or 3. But each time I read it, I understand it a little bit more. But the thing is, you don't have, I'm reminded of something a very wise Professor Arthur Shallow said. He said, you don't have to know everything. You just have to know something that nobody else knows.
Mm-hmm. Yes. Yes. Very well said. Yes. Perhaps I'm inspired by what Professor Ogure and Professor Chu said to add a tiny bit from my own experience. Professor Ogure had mentioned Yoichiro Nambu, who is somebody I have the greatest respect for. And when I was starting out in my career, I once told Nambu how much I had to learn, just like this student who just said that there's enormous amount to learn. And Nambu said, it's not that much. When I was a student in Japan, I had to study classical Chinese poetry first before I can learn physics. Others? Oh, there's the hand.
Thank you very much. My question is that when I talked to my my colleagues, my schoolmates, we think we, as young people, we think there are maybe too much young PhDs and young scholars, but there are too few positions for them to work and to pursue their scientific career. So my question is that for you very senior and experienced scientists, do you think it is a problem? Do you think it is the competition nowadays is natural for the young scholars, or is there something should be changed, or who should change it? And as young individuals, and if we want to pursue our scientific career, in nowadays, now this scientific ecology, what should we do? Thank you very much.
Does somebody wants to answer this question? Does somebody who knows China perhaps better than me? I'm sorry. No, Stephen, please.
I don't know
Stephen.
China better than you. Look, I actually felt that way when I was young. And so there's a huge process where many of the students in the 70s couldn't get jobs. And there's a weeding process, you know, a very small fraction could get jobs as professors. And I knew this, and my father was very worried that, you know, I'm going to spend, you know, 5, 6, it turned out to be 6 years getting a PhD, another several years as a postdoc, I'd be unemployed. And I told him, I don't care. I like what I'm doing. If I become unemployed after that, I'll face it when it happens. So for now, if you really love what you're doing, continue. And to be sure, there is this huge weeding out process. But in that process, you know, if you love what you're doing now, continue it, and just, you know, one day at a time is, I don't know, maybe you.
No,
Anyway, that's it's not very satisfying, but in my generation, I felt that way. He didn't, because he was a child prodigy.
Well, maybe I can answer a little bit. The number of jobs for good scientists has been increasing tremendously in the last few years in China. That's assuming you are good. In Beijing city itself, I think we have more than 500 mathematicians, far more than any other country, any city. So I don't think there's lack of job. It's a question of how capable you are. I believe the Chinese young scholars should be excited about it. It's not only in Beijing City, in Shanghai, in Shenzhen, all this. I think as long as you are capable and good, there's no problem to find jobs. It's most exciting period compared with the last 50 years that I know of for the Chinese situation.
Thank you. I'm very happy to hear that. And perhaps I could add a tiny story to this.
Let me just one more answer to the question you raised. I think I see a trend that from the AT&T Bell Lab model, it's actually a private company that support the research. I think in China, as more and more companies become successful and make a lot of money, they probably want to will invest into basic research. So I think in the future, probably there will be many more jobs that provided by some institutions that funded or by private sector, by private companies that actually not investing to to try to make some immediate application or some profit for the company, but for the long-term basic research. I see the trend. I think things like the U.S. AT&T Bell Lab or others. Well, in the future will be many, and I think our company probably one of them.
Thank you. So I don't know the time constraint. Is there some constraint for dinner, or is there time?
Yes.
Is there more time? There's more time. I don't know Professor Yao's schedule, but maybe I could tell a little bit of story to encourage the young student who asked this question. When Max Planck applied for a job in physics, he thought it was totally hopeless and he was going to give up, because everywhere he applied for a job, he was number 2 on the list. And all the evaluations said he was not as good as the number 1 guy. And the number 1 guy was Hertz, who had discovered electromagnetic waves. So every place offered Hertz a job, but not Max Planck. But look, Max Planck eventually triumphed, right? So there's a question from the back there. I don't know, this lady said there's time, but I don't know, Professor Yao?
Thank you. I'll keep it very short. I wanted to echo what was said before about the private institutes funded by private companies. I want to contribute with a positive example. I belong to an institute that is funded by Boehringer Ingelheim, which is a pharmaceutical company, but this institute is embedded and integrated to the research landscape of Austria. Now, the particularity is that this company is a family-owned, very, very large company, and this is a philanthropic endeavor. So my recommendation for the ones looking for companies to fund institutes is look for companies that are not in the stock market and are privately owned. Additionally, many philanthropic endeavors of this kind from other institutions are also doing agreement with, for example, the Austrian Academy of Sciences, with a turnover of the institution in the future to the academy itself. So it's funded for 10 years and then shifted. So I wonder if there are other successful stories like this in China or in the US.
Okay, this lady told me that there's maybe time for one question, if it's very urgent and short. Then we close. Thank you very much.
Thank you so much. Well, thank you for all the professors' great speeches and insights, especially the wonderful Q&A parts. They were so inspiring, weren't they?
Absolutely, and I have to confess that Professor Oguri's papers were part of my research when I was doing my PhD. And of course, let me also thank Professor Andonizi for his very nice hosting and very nice stories that he shared with us.
Yeah, I was listening very carefully. It was quite a brain teaser for me.
Well, Grace, welcome to our world. Nice world, but don't worry because our banquet time is approaching.
Yeah, it's time for us to replenish our energy, especially we have more great scientists with their great insights coming later.
Exactly. So we have set different locations for your dinner. So please look carefully on your dinner voucher, and we will see you back then at 19:30 sharp.
我们为大家设计了不同的餐区，请大家仔细查阅手中的餐券。按我们的餐区就餐，19:30我们准时回来。
Thank you very much. See you later.
International Congress of Basic Science. Why is it so important that all the world's greatest minds gather here again? Luckily today, our greatest minds are going to give us the answer by the upcoming panel discussion, the importance of basic science. Let's invite them. Our first guest, Professor Samuel Chao-Cheng Ting. He's the chair professor at Massachusetts Institute of Technology, Foreign Academician of the Chinese Academy of Sciences, member of the National Academy of Sciences, member of the American Academy of Arts and Sciences, foreign member of the Russian Academy of Sciences. Welcome. Professor Stephen Chu at Stanford University. He's the Foreign Academician of the Chinese Academy of Sciences, member of the National Academy of Sciences, member of the American Academy of Arts and Sciences. Welcome. Professor Yifeng Wang at Institute of High Energy Physics, CES. He's the academician of the Chinese Academy of Sciences, international member of the National Academy of Sciences, member of the American Academy of Arts and Sciences, foreign member of the Russian Academy of Sciences. Welcome. Professor Hiroshi Oguri at California Institute of Technology. He's the member of the American Academy of Arts and Sciences. Welcome. Professor Xiang Zhang at the University of Hong Kong. He's the president and vice chancellor of the University of Hong Kong, foreign academician of the Chinese Academy of Sciences, member of the National Academy of Engineering. Welcome. Professor Di Li at Tsinghua University. He's the chief scientist of FAST. Welcome. Professor Hong-Rui Tai from Cornell University. He's the former director of Institute of Advanced Study, Hong Kong University of Science and Technology. And Professor Hong-Rui Tai will be hosting this panel. Let's give him a warm round of applause. Welcome.
You can hear me? Okay. Happy that everybody's still here after a very nice dinner. And the topic we have today is the importance of fundamental science. And we are very fortunate already have two beautiful talks, one by Professor Steve Chu and one by Hiroshi Oguri, which really answered the question that you may want to ask later. So we should thank them and make this panel discussion much easier and with more free flow. The first, I think that I actually went to WeChat and look up why fundamental science is important, and come up first is a talk by somebody last year in Xi'an Jiaotong University, Professor Sam Ting. So we'll start with Sam to give us some introduction to today's panel discussion. So
it's you now. Oh. So I don't give public talks because I'm really not good at this. Before I start, I want to thank Professor, where's the Professor? Yeah. And Yifan Wang for this opportunity to express my views on the importance of fundamental science. In 21st century, we enjoy unprecedented advancement in technology, such as in the field of communication, computer, AI, transportation, healthcare, commerce, and so forth, which has dramatically affected the quality of life. What is often forgotten is the fact the foundation of this achievement was laid down some time ago by scientists who were driven by intellectual curiosity and wonder of nature and not by economic concern. So this is my little graph on research and daily life. I marked 1900s, 1950, and now. Physics is a function of distance. In 1900, we studied mechanics, thermodynamics, optics. Now we have microwave, aerospace. In the 30s, we studied atomic physics. Now we have AI, we have computers. And go to 50s, we study nuclear physics. Now we have nuclear energy. So with the accelerators, we look for particles and quarks. For larger distances, in the beginning, we have looking at the stars. Now we have navigation in timepieces. So the pyramid has grown with new application increases high, where fundamental research expands its ways. The role of basic research implies that it finds itself in the outermost corner of the pyramid. Hence, it's sometimes disregarded as being remote from daily life. Only after some time, when applications develop and public become familiar with the new phenomena, does the value of research become more understood. Experiments are of fundamental importance to the advancement of knowledge. A theory, however elegant, cannot disprove experimental results. Only when an experiment contradicts a theory will knowledge advance. The prime motivation of basic research is curiosity, the innate passion to learn something new or obtain a deeper understanding of natural phenomena. Questions such as what are the basic building blocks of nature? What make up the stars and galaxies are eternal and have inspired generations of scientists, artists, writers to seek answers and explore the unknown. The result of this research of new technology and industry have profound effect on quality of our life. So that's my little observation.
Thank you, Sam. Listening to the two talks earlier, I'd like to make one comment, in particular to Hiroshi's remark. I think many of you may be discouraged by the fact that he said 1,000 years in order for us to solve the problem, and another 1,000 years in order to show it's correct. Don't be discouraged. We look back when the early development, when they developed unification of electricity magnetism or quantum field theory, the number of physicists working is order of hundreds, maybe 1,000 at most. But now we have close to 100,000. And we all need to do is increase the number of physicists to 1 million, which probably not impossible, in fact, if the number is increasing. Then instead of 1,000 years, we can cut down to maybe 10 or 20 years within your lifetime. And how to do that? Well, like what Steve said, have good labs that allow young people to do research that's curiosity-driven and can set up new institutes, which BIMSA is one of them. And I'm sure that China will continue to grow, and I hope other countries too. In fact, in UK, molecular biology now actually moved from what they have to something called Crick's Institute, which is bigger and more people and more research funding. And so this is a phenomenon which go all over. And so 10, 20 years within lifetime, I think we can solve the quantum gravity problem. I just try to be optimistic.
Thank you.
The importance of fundamental science, I think most of you are aware of, and everybody have their thinking, and we're open for discussion for panel members here. I just want to raise one particular issue which may be more relevant nowadays. And that is the international community or the worldwide affairs situation now is very uncertain. In the United States, it's clearly, we're going to have at least 3.5 years more to go to face great uncertainties, and many of us not that hopeful. And Europe also, they just want to increase the military funding from 2% GDP to 5% GDP. And where that money coming from, I think they will look at fundamental research as one possible pocket. So these uncertainties means that we have to face and question how to face these issues. I would like to have the panel members maybe consider this, and how to focus on research, basic research, and such that we can go through this hard time. Please, it's free flow. Anybody is welcome to say something. So,
Henry, thank you. I guess it's well said, Professor Ting, about how important fundamental science and so on. And I'm sure the audience here, many of you pursue the basic science, mathematics, and physics, and so on. So I'm not going to probably, try to persuade you to pursue the fundamental science and why this is important. Henry brought this issue of the currently the polarization in this world within some country and across the countries that create a huge challenge, not only financially, but also in terms of sciences, about a lot of them about collaborations. Even mathematicians, sometimes they collaborate. So this really is a challenge. And I would appeal, our young scientists, try your best to reach out, to collaborate as far as possible. So, of course, it's not easy. But I also want to bring the other almost orthogonal, but they are coupled, X and Y, frontier. That is the AI. Now, we, human race, actually, will never experience this in the last probably 500 years. Such an acceleration of the knowledge and discoveries and so on with the system of AI. Many of my students say, well, today, if you do certain things, the AI can do a lot for you. So then actually, you always can say, well, we are basic. We are so fundamental, so AI cannot replace us. But let me bring one observation yesterday. I think one of the young awardee, maybe a group of Yang Werde published a paper about autonomous design and execution of chemical experiment. Now, what does that mean? It's really frightening to me that, you know, if AI somehow can design certain molecules or things, essentially human interaction, I mean, of course you have to define the problem, but, you know, AI can automatically design, execute, maybe analyze the experimental data and so on. Now, AI is still in the primitive age, and I think if you are fundamental enough, you shouldn't worry about it. But these are going backward to the upstream, and human intelligence are really extended in some way. We can call it a human extender. And I had the dinner 2 weeks ago with you know, one of the major companies, US AI company. And he said that he's actually training an AI agent to be his chief of staff. So one day, probably he thinks in 2 months, he doesn't need this chief of staff anymore. So think about it, chief of staff is very smart, quite fundamental in business, and yet they can. So I like to actually bring this issue because as a scientist, as a people work on the fundamental frontiers, whether it's physics or, and we're going to be positively impacted by the system of the AI, but at the same time, that challenge the very definition of human curiosity and ingenuity and creativity. So I don't have much of answer, but I like to, you know, give our audience to think about it. Thank you.
I can just make 2 comments. First of all, we should try to improve our communication skills within ourselves, also beyond our science community. For example, very often we say, everybody say that our science are actually driven by curiosity. I think within our community, it's probably well understood. But beyond our community, sometimes people will argue, why should I pay our taxpayers' money for you, for your curiosity? So sometimes this is misleading. So I think maybe we should try to change a little bit. Instead of saying curiosity, but saying that the science actually is driven by every discipline's internal logic. It is really the discipline, the field, which has to progress in a way suggested or driven by whatever the discipline itself is needed to improve or to progress. So I think we probably have to try to change a little bit our wording. My second comment is that even though we are in a very difficult situation geopolitically, but still we can and we should do more. Because even during the Cold War, the only field which had very good communications between the former Soviet Union and the US is the science collaboration, and was kept. And everybody understood this is probably the only few channels you should keep the dialogue. And this kind of dialogue is very important for peace. So I think our scientists and our community, even though encountered enormous of complication difficulties, but should try our best to improve our collaboration, and also in addition to spread out the message from our community to the politicians or to the general public or the media that international collaboration among scientists is extremely, extremely important and vital. And this is also our contribution to the betterment of the world.
Thank you.
May I? So as it has been said earlier, we are in some sense talking to people who are already convinced. And so I don't have to tell you how important fundamental science is, because most of the people here are already bought into that. So I regard one of the purpose of discussion today is to sharpen our logic. Namely, that when we go out and somebody else asks you why fundamental science is important, you'll be ready to come up with a very cogent answer. So with that in mind, I'd like to contribute 2 ideas. So for you to sort of explain why fundamental science is important. One is the following. So what we are doing is to expand human knowledge. We are expanding the boundary of known and unknown. So thousands of years, we have learned quite a bit about nature, but there are many, many more things to learn. And as we expand the horizon of our knowledge, horizon expands and more unknown comes in. And now, in order to stretch this horizon, new technologies are needed. New mathematical techniques are needed. New language has to be developed, but also engineering and technological advances are needed. So in some sense, the research of fundamental science inspires new development of technology in a way that ordinary industrial research would not. And this has produced lots of technologies that have actually improved human life. Just to mention a couple of them, the CERN, where thousands of scientists needed to communicate large amount of data, they developed a World Wide Web. And of course, that has really changed human life. Either positive or negative, you could say, but it did change, had an impact on civilization. And also, there are many medical technology, the protons, accelerator, etc., that has found application to medicine and saved many lives. And those would not have happened if we, human as a whole, didn't try to push the boundary of known and unknown. So that's one of the very tangible impact of fundamental research. And another thing that I mentioned, and this is related to the speech I gave, which is the importance of curiosity-driven research, which has already been mentioned. But in some sense, curiosity-driven research are also value-motivated. The researcher have looking for some valuable research. And so then you can ask, what are the valuable scientific research? And I gave partial answer to that question in my speech, which is where I quoted Henri Poincaré's book. And this actually resonated me very well because one of the reasons actually I have been fascinated by mathematical science in particular is that discovery we make has lasting impact. For example, the mathematical theorem, in some sense, is an eternal truth. And in addition, what Poincaré said is that you should look for science that has broad impact, not only the original aim, but have a lasting impact and eventually many areas. And often that leads to unexpected applications. And as I said in my speech, that application can include industrial application and application to improvement of life in unexpected way. And again, there are many historical examples going back to Maxwell's unification of electricities and magnetism leads to discovery of, for example, telecommunication and many other things. And so I think in some sense, the exercise of fundamental science is in this way stretch our stock of human knowledge. In some sense, these knowledge are like fossil fuel that we are in some sense, modern technological company are burning fossil fuel. And if we don't replenish this, then we're going to run out of fuel for the further development of human civilization. So that's another way that maybe we can make a case for the importance of fundamental science. Thank you.
Thank you.
I'm trying to think of what I can add to this, and I think of several examples that have it's really hard to predict when some curiosity-driven research will actually turn into something useful. And it depends really on when you start the clock. For example, with Sam Ting's history, you may have noticed that the difference between the development of quantum mechanics and its application to semiconductors was about 1 year. Bell Labs realized very, very quickly, or 2 years, that it's going to be very useful. But then the question is, how did quantum mechanics come about? And that history was very different because it started long, long ago with people measuring spectra of atoms, right? And didn't know what to make of it. And then simple models of what the spectra was. So the gestation period, it depends on when you start the clock, but it usually goes way back. And so the idea that, now, I'm hoping it's not going to take 1,000 or 2,000 years to marry gravity with the quantum world. It may, I doubt it, nor will it take 10 years. It's like saying, well, it took Einstein from 2004 to 2015. That's, what, 11 man years. So you just hire 11 more people and you can get it in 1 year. No, it doesn't work this way. There's certain things that have a gestation period, and there's certain things that have to wait for new data and new technology. And so it's, but you know, NMR, you know, the study of the fundamental properties of nuclei and atoms, and starting in the 30s. And who would have thought it would have led to nuclear magnetic resonance imaging? Now, Purcell actually did think of it when he was inventing it, because 1 year after that, he actually did a first experiment with NMR imaging. But it's when you start the clock, and the clock started long before that. And so that's another reason why you have this curiosity-driven research, and you have to, this is laying the groundwork for other people to come along. And I just want to conclude that the most thrilling part of, I found when I was in high school of taking physics, it was very different than biology. Biology would describe things. You know, what does a leaf look like? What is it? And it would name things. And it just, you know, Feynman has this beautiful section in his lectures about, you know, just because you know the name of it doesn't mean anything. You don't understand anything. And the beautiful thing about physics is what you're searching for is a deeper understanding that becomes very cumulative. And it's not like measuring number of particles, you've run out of the number of particles. No. There's, as you described, you're going for deeper and deeper understanding of what was going on. And so that thrilled me to death that as physics was doing that. It's just not a descriptive thing, and it gets deeper and deeper and deeper. And each revolution has to incorporate the last revolution in that. And so it was thrilling for me to do that. I hope for you young people, you find it also equally thrilling that this is this cumulative knowledge based on ground rock stuff that is, and it's fundamental science. That's the foundation of the ground rock. Thank you.
I just realized that on the stage, I'm extremely honored on the same stage with Professor Ting and all the luminaries. I'm relatively young and probably too naive. So in response to Professor Tai's initial question, so under the current sort of change and uncertainties worldwide, I'm extremely optimistic about both the sort of job prospect for physicists in China and for the development of fundamental physics for the immediate future in general. So our telescope, the 500-meter telescope, is the largest antenna ever built. But it's a successor of another great science and engineering wonder of the 20th century built by Americans in 1963. That's called Arecibo. And the discovery from Arecibo won the Nobel Prize in Physics in 1993. And the reason that Arecibo got built is this great space race between Soviet Union and United States. In 1957, Soviet Union successfully launched the first man-made object to go around the Earth, that's Sputnik. And that so-called Sputnik moment spurred two immediate reactions. One is the establishment of NASA. Another is the funding of Arecibo telescope from this newly founded national agency called ARPA. ARPA was later transferred under the profile of Department of Defense. It's DARPA. So I think maybe for some of the students here probably know that name. And it was built as a relatively cheap and probing sort of regime-changing scientific instrument, not even for astronomy, but the astronomers sort of immediately take over. You realize you build such a big radar, it's also sensitive for collecting all sort of unknown waves from the space. So coming into the current days, like the FAST telescope and our colleagues in Canada, in US, we keep finding unknown mysterious signals. We don't even know which part of the theory we should put into, like this extremely bright radio burst that is so bright it concentrated decades of solar radiation in 1 millisecond, and that's enough power to power the current global society for like 1 trillion years. And we don't know which object it comes from. We don't know what physics it required to produce such so-called laser-like radiation. So that reminds me of what Lord Kelvin famously, purportedly said, that the grand building of physics was already built, but there are two clouds, right? The one for thermal radiation, another for the transport of light. That's the ether problem, which in turn gave rise to quantum mechanics and relativity theory. So that sort of goes into the modern physics we know. So I'm a pure experimentalist. My math is only average, and I always follow the much smarter minds on stage in physics. But my greatest hero is this one astrophysics, Fred Hoyle. So at the time, there's a bunch of the astrophysicists try to figure out the energy source of the sun. So it has to be through nuclear fusion. Because there's this annoying problem that once you get to carbon, the reaction between sort of the heavy helium-4 fusion, the cross-section was too small. So Fred Hoyle has such a great insight. He said, well, instead of a two-body reaction, you can have a triple reaction, that's triple alpha process. So that overcome that hurdle and leading all the way to the make of heavy elements. But at the time, there's no observation and no experiment. So he went to Caltech to talk to Fowler, this great experimentalist. And Fowler agreed to do this experiment, but you cannot do fusion in lab, so they do fission. So the reverse is also true. So you can break up a carbon-12 into three alpha particles. And the most amazing part of that story is that they eventually measure the cross-section at, I think it's 4.8 MeV, which is very close to Fred Hoyle's just like intuition, because he just calculated this nuclear reaction. So that's sort of my goal, and sort of a goal of a lot of experimental physicists and astronomers in China, is that now there's not only FAST, there's also the InSight Hard X-ray telescope operated by Professor Wang's High Energy Institute. There's the great cosmic ray experiment, the LASSO experiment. There is the Einstein probe. There is the Wukong satellite. So there's this collection of new experiments, and collectively we are finding so many new and mysterious phenomenon. I think someone much smarter than myself will come up with new physics, new theory. I used to think optimistically, maybe that's before the end of my lifetime. Now I'm even more optimistic. I think it's in the next 5 to 10 years, maybe with the aid of AI, like Professor Zhang just mentioned, we may be seeing some completely new regime that to solve, for example, origin of cosmic rays. And for example, we are in the process of confirming the existence of amino acids in the interstellar space, and that's through up the chain of nuclear fusion predicted and tested by Fred Hoyle. Thank you.
Well, Dr. Lee mentioned it's a great story about the triple alpha between Fred Hoyle, Salpeter, and Fowler. Theory, experiment, it's done literally weeks. But now maybe anyone have a comment on each other you want to make? Please.
I want to turn a little bit back to AI because it may have will have, I think, a bigger influence than the internet. And I use it every day, and it took me with a little help. I could figure out how to get Google to work with a colleague of mine. but the AI has wonderful things, wonderful capabilities, but there's a danger, and the danger I see is mostly with young people, because increasingly they will turn to AI to help them write a paper, or maybe write the paper for them. And they say, well, you know, we have to publish in English, and it's not my native language, but it's going to be more serious than that. That because, you know, people whose native language is English, like in America or Great Britain, they're turning to AI. And my big fear is that in the act of writing, you're forcing yourself to think clearly and to order your ideas. Good scientific writing is the same as good writing in general. And as soon as you start to use this too much, you lose the ability to order your ideas. And if you become too dependent on AI, I'm a little worried that, as even for myself, that you get intellectually lazy. But now older people, they've had some habits, and so this is it. But I'm mostly concerned with younger people, and I watch students, especially undergraduate students and below, use it more and more and more, and they're forgetting. And so it's replacing writing, which is a discipline and how to think. And I'm very concerned about that. So just a comment, and I hope that you young people don't use it to write your papers.
Thank you. Yes, please.
I want to also address some of our young colleagues here, young students here. And for the senior colleagues, you have a job as a professor and a researcher, and so on. You are doing fantastic science, and funding may be a little bit sometimes worry, but generally career is there. But for a young student doing PhD or a postdoc, often in this part of the world, I would say, especially in China or Asia, people tends to parents and themselves say, well, I'm doing science, I really like it, but after 5 years, I get a PhD, I need a job, right? And thus, you know that probably 20% of our PhD students will continue as a researcher or professor and so on, but 80% will do something else. All I want to say is, in fact, you choose this course for the next 5 years for your PhD or postdoc work. It will be a tremendous help in your later career, whatever you do. Maybe you're a banker. I was visiting London early this year, and some of people told me that the banking industry in London likes to hire scientists because they think deeper, and maybe they need a little bit 6 months training of the business, but when you put them into work, they think deeper, clear, and so on. So there are all of these trainings at very superficial level gives you a huge advantage later on in life as well. I also like to bring the other aspects I personally find is interesting is a personal fulfillment or enjoyment. Now, you may say, well, I'm doing a really cool experiment. From that, I draw the enjoyment. But at the same time, it reflects some of the daily life as well. I mean, some of you probably, if you're driving in the road in the raining day, you brake it, you brake earlier and so on. Now, some people, without learning the physics, they know that's instinct. They drive long enough, they have instinct. But the physicists will say, well, because of the friction coefficient is not that high, so therefore you better to brake earlier so that you become safe. So those little things in the daily life where we see the pyramid Professor Ting talk about in daily life, actually little by little, you find it quite enjoy that you know this knowledge, and that helps you to appreciate those details in life. And so I find it quite interesting. Now, of course, many of you still say, well, I need a job. And of course, this is after you get a job and you still can. So those parts, I think being a scientist, whether physicist or chemist, a mathematician, you do have that really intellectual enjoyment afterwards as well. Thank you.
Thank you.
Yeah, so I just wanted to comment very briefly about what was being said. So some of you, I guess I heard some anxiety from students who asked that question. And even despite what Professor Chu kindly told me, said about me, I also had to struggle, and especially to explain to my parents why I would like to go into that direction. My parents both my parents did not go to college, and so they didn't have any idea of what academic life is like and what research life would be like. And so when I was in high school, they expected me, I was good at math and science, so they expected me to go to medical school. And I had to explain to them that why you can have meaningful life if you go to science, and there can be a career you can build up. And I felt that it was actually extremely good exercise for me, that I was able to internalize why I want to do this and what kind of plan I have. And so for those of you who have sort of concern about this, this might be one of the exercises that we want to do, that reflecting on why you want to do it, why is it important, why do you think you can have a meaningful life by going to science? And for me, this was a very helpful exercise. And so the other thing, which also I want to mention related to this, I keep track of my former students and where they have gone. And half of them have remained in academia, and they now have tenure track or tenure position in prestigious university. But half of them went to industry, and they are all successful. Many of them are much more money than I do. And one of the reasons that happens is that this process of getting doctor's degree give you very precious experience of producing something valuable from nothing. So I'd like to remind you that doctor's degree is given to people who have produced the new knowledge to the cathedral of knowledge that a human has built for thousands of years. It's a wonderful thing to do. And the purpose of defense committee is to judge whether this new knowledge has merit or not. So this is an experience for you to add new knowledge that nobody else in the world knew and add it to that. And in fact, when I was a graduate student, the first time I wrote a research paper, I had this wonderful experience. I had this writing trying to solve some problem, and I found what I considered to be a beautiful solution to this problem. And I was going back home and looking at the night sky and thought, well, in this entire world, only I know this truth. And so I hope that some of the students who are interested in going this direction will have this experience.
Please.
Just speaking of jobs, there are certainly more and more astronomy jobs in China for physicists. So I recently become the chair of the Department of Astronomy in Tsinghua. It's such a new department. It was established only in 2019. And before year 2000, there are only 2 departments of astronomy in China. Now it's close to 20. So by my estimate, because there are a few is in the process of being established, so in 10 years from now, we'll probably get close to 40, which is a reasonable size scale for the sort of the physical science in China. And my personal experience is that my most successful and best student come from physics background. I have a PhD graduate a few years ago, so he was a physics major in Tsinghua University, and now he got national funding. He won the Damo Orange Award a couple of years ago, and another of my students from UCAS just won the National Postdoctoral Fellowship Award, and he was a physics major. So the physics is true. I mean, it does teach you a lot of a very fundamental science of how to carry out research. So I think it's great prospect for a lot of the students here.
I just want to endorse that statement. Fundamental physics and astronomy, astrophysics, cosmology are intimately related. So many particle physicists have moved to astronomy, cosmology, astrophysics. And then the knowledge is very, very transferable. And I'm very happy that now there's 20 department of astronomy in China. There will be more. So you should think about that direction as well. And it's very exciting physics to do there just as well. So yes, Steve.
I also, we're telling you you've made the right career choice in your education. I've always regarded physics as the best liberal arts education you can possibly get. And so you think to yourself, what, liberal arts? I said, no. What the best liberal arts education is an education where you have the ability to say, I want to learn something, and I have enough confidence to teach myself this. And so, and it's, when you're hearing people talk about how physicists become good astronomers, actually physicists become really good biologists. I've been in biology for now 30 plus years, and I slowly began to realize that many of the Nobel laureates in biology are actually physicists.
Yeah.
And the ones I produce that go into biology, they look at the world differently, and it's something really good that you should take to heart. That your training is going to be very, very precious because it is so rigorous and it doesn't mess around, and appreciate that you can do things, and hopefully you have the confidence to say, I wanted to do this, I want to learn that. And so it is a great education for all of you.
Right, yeah, so I just wanted to add that when I talk to actually people who went to industry, they say that one of the things that they appreciated in industry is the approach for physicists to go to fundamental principle. So when you encounter some difficult problem, it doesn't have to be actually scientific problem, but then you try to understand going down to fundamental problem, and then try to build that from bottom up. And such experience is given in physics research, and so that might be one of the ways that physicists are very useful, not only in physics, but in biology also.
Certainly true. Many physicists move to biology. I mean, Max Delbrück, Gilbert, Francis Crick, and Steve, it's a long list. It's very successful, sometimes both directions. So you should think about it.
and it doesn't go the other way.
It doesn't go the other
It's like a diode. If you're a good biologist and you say, I want to be a star physicist, I don't actually know of many examples or of any, right?
None that I know of.
So again, it's
one way.
So again, it shows the strength of the training and the education.
I just discovered actually this panel is made by 100% physicists. So no wonder actually we resonate with each other and also resonate with some of the colleagues here. But let me broaden that a little bit, more basic science, come back to this. We can all agree basic science is important, is not only for knowledge creation and so on, but also it's as simple as a human aspiration that for many years we want to learn things, we want to go to Mars and all of this. That actually is something very, very important for humanity to develop and so on. But being here with 300, 400 colleagues here, we're all fundamentalists and doing things and so on. But that doesn't solve one problem. The problem is we're facing today. In US or in other part of the world, that funding, people think that, well, if you're doing something useful, and we would like to fund it even in Hong Kong. I can see a lot of signature of that. When I do fundraising, people always ask me, well, if you do this for medical treatment, we would love to donate to you. But if you do cosmology and so on, well, what is that useful for me? No, this is for laymen in the society, and some of the people in for example, now US, we see there's a major funding cuts and likely fundamental science will be affected and so on. So that brings a very important issue, that is how scientists to reach out to the public, to educate, lobby, and whatever that we have to reach out. Otherwise, we can resonate ourselves here within 400 people, but it doesn't make much of the fact that I remember when I was working at the UC Berkeley, and I also have a joint appointment at LBL. Steve was the director of the lab. I'm not sure Steve was responsible for that Saturday morning science talk. I don't know, maybe he initiated or some of colleagues initiated. It was beautiful. All the citizens from Bay Area, come to LBL and listen. All the scientists have to give these talks in a layman term, very simple language and so on. And that creates a huge impact, not only for parents, but also generally when you have scientific initiative or even when you build something and people used to could rise up to against that, but now that could be the other side of the equation where people say, well, science is important. The same thing is true. We like to see more scientists going to different avenues, like Steve was as a Secretary of Energy in the government. He made a tremendous impact for the energy, not only research, but also industry transformation and so on. So I remember 10 years ago, somebody told me that in US, Congress, only one actually congressman are basic scientists. There are some are engineers. But if you think about one out of maybe 200 some congressmen, this is very little. This person can jump up and down and so on, say science is important and so on, but he only have one vote. So what I'm trying to say is reach out to the public, to some extent going to the government, even talk to politicians really can make a difference in terms of how the science, impact the world and, as simple as secure more funding for our community. So that's my 2 cents.
Thank you. Oh,
Actually, it was a very conscious effort on my part to do the Saturday thing. Yeah, and so because I thought it was very important for scientists to reach out and to show people how exciting it was. We also had programs to reach into high schools, and because high school teachers especially, it's a thankless job, And so I said, we have to give them moral support. We have to go and into their classroom and tell them how important it is to remind them what they're doing, because we all started in grade school, junior high school, high school. I mean, it's usually where, if it's not our parents, it's that inspirational teacher in K through 12. And so this is another thing that is very, very important, that you think about how to reach out. And you know, despite all this crazy stuff going on in the United States, there is one good thing about it, because we were taking things for granted, right? And we should really think about, ultimately the basic science leads to things. What drives us is really curiosity. And by the way, we shouldn't say that only physics does basic science. There's basic chemistry too, even basic biology, but basic science in general. And so it's very important to think about what you're doing and to talk to a lay audience about what you're doing, because it actually helps you think clearly about why you're doing it, as you pointed out.
Oh,
I'm wired.
it's okay.
You're automatic.
Yeah, this is a very impressive discussion between physicists and biologists reminded me an equally important issue, whether you want to be a theoretical physicist or an experimental physicist. When I was in graduate school, I had very good grades. Like all the people who has good grades want to do theoretical physics. So I started with Otto Laporte and with Ken Case and with George Uhlenbeck. One day, Uhlenbeck got all his students in his office, have a tea together. He said, if I would do my life again, over again, I would be an experimentalist rather than a theorist. Uhlenbeck is a very well-known physicist, so I was quite surprised. I started with him for about 4 months. I asked him why. He said, average experimentalist is useful because you always measure something new. Every theorist is not. That was his sentence. He said, you can count on your finger. You have less than 10 physicists in 20th century who really made a difference. So after this little conversation, I took a walk in the garden and then went back to see him. I said, you are right, I'm leaving you. And so I went to Berkeley to do my PhD degree. I know absolutely nothing about experimental physics. I don't know a coincidence circuit or diode, but you quickly learn. Often people think incorrectly, if you know how to use your hand, you should be experimentalist. That's certainly not true. Most of the, in fact, all the Nobel laureates I know in experimental particle physics all knows a great deal about theory. For myself, whenever, before I start an experiment, I always go to see Steve Weinberg, whom I've known for years, and Richard Feynman, and also Panofsky. I talk to them, listen carefully, but seldom do what they say. I think for experimentalists, you do need to understand theory, but more important, to keep your own judgment. So if you are a theorist now, remember what I said tonight.
Thank you. Okay, So we will now open to the floor. We will welcome questions. Let me.
While you're thinking, I have a very funny story to tell you. Cian Yang, many years ago, and he said to me, Steve, I have to tell you that I really wanted to be experimentalist. And I said, what do you mean? Even when you were an undergraduate, he was a classmate of my mother, you were a brilliant mathematical person. It was clear, everybody thought you would get, my mother said, we all thought he was going to get a Nobel Prize. And so he goes and so I said, why do you want to be an experimentalist? You're so brilliant mathematically. And he said that experiment is the heart of physics. And I wanted to be at the heart of physics. And he went on to tell me, he tried desperately to become an experimentalist. And he said, at the beginning, there are two jobs when you have a vacuum chamber. One job is to look at the meter and go tap, 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 and the other person squirts acetone. And he says the skilled job is squirting acetone. The stupid job is tapping the meter to see if the thing flickers. And he said, I never graduated to the skilled job. and then he said, and it got really bad because when there was a vacuum implosion, it got to be where there's a bang, there's a yang. So then, and he goes on. So he's struggling, and finally, I think it was Edward Teller says, "Look, you're brilliant. You work with me. Stop this experimental stuff. You'll get a PhD in 1 year," which he did. but again, he was telling me, it is in the heart of science, in the heart of physics, and it really. I think is true, being an experimentalist.
Yeah, that's a question there. Yeah.
Thank you, professors. And I have two questions. The first question is, what do you think is the future of experimental high-linear physics? And the second is, what are your suggestions for the young people who want to devote themselves to the experimental high-linear physics? Thank you.
I think Yifang.
If you look back the history, in 50s and 60s, we had a lot of experimental evidence, new particles, and we don't have a theory. So that was a golden time for theoretical physics student, and you can contribute to the establishment of the standard model. And indeed, many people made their achievements. After that, of course, we had a lot of experimental, very important discoveries, but many of them are actually to prove that the theory is right. And we kind of follow the habit that every experiment have to come up with a theory prediction, and then you try to prove it. This is true up to 2012, when Higgs was discovered. Now we end up no new theory to tell us exactly what to do next. But of course, you cannot think that the future is over, that if you don't have a theory to tell you what to do. Indeed, this is the other way around. When you have no theory to tell you exactly what to do, that's your time as an experimentalist. And indeed, I think in the future, it is the time for our experimentalists to tell the world what is the next level of the physics, new physics. So, of course, this is just general kind of ideas, and you have to look down, and there are several major portals for the new physics. I think Higgs is one, neutrino is one, and dark matter, dark energy, and astrophysics is another one. Of course, does not exclude many other portals. I think it is actually up to experimentalists to come up with the idea of what's the next. And I think we are roughly, let's say, around, we are very, very similar to the year of 1560, but some kind of reverse kind of situation. There we have no theory, and now we have no experiment. So I think it's a golden time for us.
Okay. Actually, we have heard about end of physics many times in the past century, so don't worry. The future is still ahead of us. Next question, we have one more. Yeah, sure. Yes.
Hello, professors. I want to ask, what is the boundary of using AI, and in what extent can AI help us to research the physics?
Want to answer?
The question was, to what extent can AI help physics? I don't want to do all the talking, so you can answer, and then maybe I chime in.
I don't have an answer, but I can tell you, 7 years ago when I left Berkeley, one of my students in my group told me that there are some people talk about if you have some, let's say, astronomy or whatever, if you have enough massive data, and AI may be able to draw that F equal to ma type of equation out. I was frightened. So that could be a possibility. That means actually there's something comparable to humans' ingenuity could come to the reality if the AI really powerful and so on. But I haven't seen the evidence yet. But that's what my student told me 7 years ago, and I haven't checked anything. But that would be interesting for astronomy or high energy physics if there are massive data and a lot of experiment, and somehow AI Newton is behind it, and boom, there's something come out.
Okay. Time is running out. Maybe one last question. Somebody? Okay. Urgent question, obviously. So.
Thank you. I have a short question. I have just entered a PhD in grade 1. Many of my classmates they have not continued education in physics. Maybe there are many young people here, but maybe only a small amount of us will continue in education in the physics research, because maybe we have many options after we graduate. We can, as the Professor Zhang said, we maybe can go to some companies to make a fortune. We can go to research. We can go to financial, something like that. But I mean, what do we? How do we choose science? Because maybe only less than 1% of us enter the research can do some real important thing. Maybe we study for decades, but we didn't do something important. Yes, thank you.
Okay, well, it's a very personal question. I think the answer depends on what you value in your life and what you want to achieve in your life. So then, if ultimately what the question is, what makes you happy? Is earning more money makes you happy, or learning the truth of the universe makes you happy? So what makes some people happy? There is actually an answer to that question answered by Aristotle, actually. And so his answer is that the person becomes happy when that person fulfilled his or her capability. So the question is, what do you think is your capability? Is it understanding physics, doing research, or what is your passion? So that's the only question, that's the kind of question that each of us has to answer.
Okay. Okay, let's thank the panel for this lively discussions, and enjoy the rest of the evening, please.